In this video, we're going to be talking about the concept of limiting a reactant, which is a way to figure out how much product is going to be made when I give you the masses of every reactant involved. Again, we're going to need a periodic table. You're going to need something to write with, something to write on. A calculator would be helpful. And once you have all those ready, let's go. So I think that a good way to start out a limiting reactant conversation is with something that you're kind of familiar with. So we'll start off with just an ordinary meatball sandwich. So here's the equation for the meatball sandwich that I want to make. 1 roll, 5 meatballs, 3 slices of cheese, whatever type of cheese you want, and 2 scoops of sauce will be a sub. Now, if I'm a sandwich shop, I generally tend to buy things in bulk. So let's say that I have 2 dozen rolls sitting around, 125 meatballs, 78 slices of cheese, and 100 scoops worth of sauce. I want to know how many subs I could make from those ingredients. Because what's going to happen is I'm going to start making them, and eventually I'm going to run out of at least one of my ingredients, and when I do, my process is stopped. Right? So the way we're going to look at this, I'm going to look to see how many subs each of those things can make on their own. Right? So if we look at rolls, 2 dozen is 24, so we have 24 rolls. The ratio is 1 sub is equal to 1 roll, so I can make 24 subs out of all the rolls that I have. For the meatballs, 125 meatballs, the ratio is 1 sub to 25 meatballs, so I can make 25 subs from all the meatballs that I've got. 78 slices of cheese, 1 sub is 3 slices. We can make 26 subs from all the cheese. And then finally, 100 scoops of sauce. 1 sub is 2 scoops. I could make 50 subs from that. So based on this, what it seems like is as soon as I've made 24 sandwiches, I'm out of bread and my sandwich making has to stop. Right? I'm going to have a little bit of meatball left over. I'm going to have 5 meatballs left over. I'm going to have 6 slices of cheese left, and I'm going to have 50 scoops of sauce left over from what I started with. But that is the idea behind limiting a reactant. The rolls ran out first, and when I run out of rolls, I have to stop production because I can't make any more. Right? So that's what limiting a reactant is. The idea, again, is that when you have a reaction, the reaction will keep going until one of the reactants runs out. When a reactant runs out, reaction stops. The one that runs out is our limiting reactant. The reason why is because it limits how much product we can make. It puts the cap on the limit. Now, whatever other reactants you may have left when that reaction finishes, those are called your excess. Right? Excess means that you have more of them. So the idea is that we want to be able to identify which reactant is limiting, how much product will be made, because whatever amount the limiting reactant makes is the amount of product the reaction will have. And then we have to figure out what's left over and eventually how much of it we have left over. Right, so let's go through the process of figuring that out. Now, before we kind of get into that though, let's talk about why have excess in the first place, right? Why don't we just mix together the exact amounts of each reactant needed in their perfect stoichiometric amounts so that we have nothing left over at the end? Why don't we just do that, right? Well, there are a few reasons why we might want to have an excess. The first reason has to do with the rate of reaction. The more reactant you have, the faster the reaction progresses. Right? So the larger the concentration, the faster the reaction, which means we'll be done quicker. So this is an example of what's called kinetics, or reaction rate. What you'll also see, and we'll get into this later in equilibrium when we cover something called the Chatelier's principle, is that if you greatly increase the amount of one of the reactions, you can actually cause it to make more product than it would normally make under those conditions. Because remember, not every reaction goes 100% of the way to the finish. Some of them only go part way. And the more reactant you have, the farther along that reaction will progress. So we can actually make larger amounts of a reactant. So, for example, the Haber process, which is how you make ammonia. That reaction doesn't produce a lot of ammonia because it's not very favorable. But if you increase the concentration of one of the reactants by a lot, you can actually force the reaction to make more ammonia than it should regularly, right? And that's valuable to us. The other reason why this is valuable to us is certain chemicals are expensive, right? And if a chemical is expensive, I want to make sure I use all of the expensive material, right? If I have something that's expensive and something that's cheap, and if I'm going to have something left over, I'd rather have the cheap one left over. Right? So, for example, if I had hydrochloric acid and aluminum foil, hydrochloric acid is actually rather expensive for me to acquire, but aluminum foil is cheap. So I want to use excess aluminum foil to make sure all of my hydrochloric acid, the expensive stuff, will make the product. Right? So those are some reasons why we would have an excess. Now here's how we figure out limiting a reactant. All we do is we do two problems, and I'm assuming I'm giving you two reactants. If you had three reactants, you do three problems. You start off with the amount that you're given for each of the reactants, and you convert it into whatever the question is asking for. Right? So if it's asking you for like grams of CO2, then you convert both reactants into grams of CO2, because that's where you have to go anyway. Right? So do two problems, go to the same endpoint for both of them. Whichever reactant produces the least is the limiting reactant. That smallest amount is how much of your product you're going to make. Do not add the amounts together. Do not subtract the amounts. Those are two common mistakes people make. You just pick the smallest answer, and that's your final answer. Now, one little hint is that when you have these different amounts of reactants, the smallest amount of reactant that you have in terms of grams is not always going to be the limiting reactant. What's going to happen is that mole ratios and molar masses will come into effect, and those will change which one might be limiting based on your initial observation. So let's try an example of this. So our example here is we are adding copper to a solution of silver nitrate. Gee, I guess that sounds a little bit familiar. If I add 1 gram of copper wire into a silver nitrate solution that contains 1.45 grams of silver nitrate, how many grams of silver am I going to make? So what you're going to do is you're going to do two conversions. The first one will be AgNO3 to Ag. The second one will be Cu to Ag. Do those out, pick whichever one is smallest. Pause the video, get an answer, and when you think you have the answer, pick it back up. Okay, so for our silver nitrate conversion, 1.45 grams of silver nitrate, turn it to moles, so we divide it by its molar mass, which is 169.88. The ratio is 2 over 2. And then we have to convert that into grams of silver, so times its molar mass, which is 107.87. And that gives us 0.921 grams of silver if all of the silver nitrate reacted. Now for the copper, 1 gram of copper divided by its molar mass, which is 63.55, times the mole ratio, which is 2 over 1, times the molar mass of silver, which is 107.87. That gives us 3.39 grams of silver if every last atom of copper reacted. Based on this, silver nitrate is our limiting reactant because it produces the least amount of product. And the 0.921 grams is our final answer. That's how much silver this reaction is going to make. Right, so that's limiting reactant. Do two problems, pick whichever one gives you the smallest answer. Our next video is going to cover how to figure out how much excess we have left. So in this case, copper is our excess reactant. How much of the copper wire do I have left when this reaction is done? So I will see you for the next video.